Okay, picking up from there. Wasn't an ideal place to stop, but my camera cuts off every 15 minutes, so, or at least it starts a new video, so I try to control that. So here we are. Again, we're trying to solve for v dot squared, this entire expression. So I've moved the 2g over, I've moved the pi squared and the d to the fourth over. I'm going to divide then by the other stuff. Alright, so dividing by the 16, we can simplify that in a second. And then dividing by this sum, so it's going to be 1 because I've moved the 2g out already, plus f L over d plus sum KL. Yeah, I think that's okay. Right? Now notice this, if you look here, right, now just to mention, if we didn't know the diameter, if we were trying to guess the diameter, notice this becomes a fifth order polynomial, right? I've got a d, if I distribute this in, I've got d to the fifth here, I've got d to the fourth there, so you just multiply everything by d to the fifth, and that ends up putting, you end up with, if I multiply everything here by d to the fifth, I've got d to the fifth here, this is constant and this is d, so if you're doing a minor loss problem with where you don't know the diameter, you end up with a fifth order polynomial in the energy equation. And you have to have some kind of, I would suggest a computer to either graph it and find the zeros, or use a polynomial solver to find the zeros. Somehow you'll have to find the zeros of a fifth order polynomial. It kind of shows up here, but the good news is I know the diameter, so I don't have to mess with that here. Okay. Now if I simplify this, I don't know if I want to simplify this. I mean, you could simplify the 2 over the 8, or 2 over 16, that's 1 over 8. But I think otherwise we're okay here. Okay. Yeah, I think otherwise we're good there. So I know everything here, and I'm sure there's lots of more elegant ways you can simplify this algebra. Okay. Debating on whether I want to go to the new page or not. We can go one more step here. Let's say v dot is equal to, we'll go ahead and do a little more simplification. Square root of, so let's say, I'm going to rearrange the top just a little bit. z1 pi squared d to the fourth g over 8 times quantity 1 plus FL over D plus sum K. Okay. All right. And what the heck are we trying to do? Well, again, I've got a guess for my F value. Now I need to find my V dot, and then I'm going to go back. Once I've got a V dot in hand, I'm going to go back to the loop and see how we do. Okay, so I need to find v dot, so I'm going to be plugging things in here. Okay, so v dot is equal to square root of a whole bunch of stuff. This is going to be fun. Fun's a relative term, right? Z1 we said is 5 foot. Pi squared, just going to leave that as is. That comes out of our calculator. Diameter to the fourth, that is 3/4 of an inch, that's 3/4 divided by 12 feet, and that's going to get raised to the fourth power. G is 32.2 feet per second squared. And then everything in the denominator, that's 8 times quantity, this is going to be 1 plus, again, we're guessing, we're just going to assume completely turbulent, and that's going to give us an F value of approximately 0.017. L over D, we said it's a 50-foot hose divided by the diameter. Again, the diameter is 3/4 inch divided by 12. That's feet. That's L over D. And then plus the sum KL, we said was, we're estimating that to be about 2.6. All right, square root of all that stuff. Wow. All right, there we are. There is some simplification you could do here, right? Obviously, you can turn this into a number, this into a number, you can turn the whole numerator into a single number. In fact, maybe we do that. Let's do that. let's simplify this just a bit. Okay, so v dot's going to equal, let's do the numerator, square root 5 times pi squared times, let's do this, 3, well, let's say 0.75, that's 3/4, 0.75 divided by 12, close parentheses. Now before I hit anything else, I need to raise that to the 4th power. Okay, and then multiply by gravity, 32.2. Okay, so the top numerically ends up being 0.024246. That's too many digits, but that's okay. Let's look at the units here. This is feet to the 4th times feet, that's feet to the 5th, times another foot, that's feet to the 6th. Feet to the 6th divided by seconds squared. What the heck does that measure? I don't care. It's just a constant. It doesn't really matter what it measures. Divided by, alright, so I'm going to distribute this 8. Alright, this is 8 plus, I'm going to leave my f alone here. This is 0.017, but I'm going to distribute my 8 to this quantity here. Alright, so I'm going to leave the f alone, but I'm going to put the 8 in this quantity. So this is 50 divided by let's just do this other one. This is 0.75 divided by 12. That's the diameter in feet. I'm going to invert that, multiply that to 50. So that's 800. I'm going to multiply that by another 8. This is 6,400. This is this quantity times 8. So this f value times 8 times this quantity. Plus 8 times this 2.6. 8 times 2.6. 20.8. Now why in the world would I do all that? Well, because this doesn't change. This doesn't change. These won't change. The only thing that changes here is this guy. This is my f value. You could add the 20 to the 20.8 and the 8 together if you like. That's okay. Maybe we do that in the next step. Anyway, now I can actually find v. It's a lot easier. Units are going to work. I got feet to the 6th divided by seconds squared. Take the square root. That's going to be cubic feet per second. I think we're good, guys. Let's find a number. Okay. Let's go ahead and do the denominator first. So I'm going to have I'm going to do that complex term there in the middle, 0.017 times the 6,400. And I'm going to add to that the 20.8 and then also add to it the 1. So the denominator is 130.6 with this f value. I'm going to invert that and then multiply that to the numerator. Multiply by 0.024246. Okay, and I'm going to square root that. It doesn't seem like much, but this is cubic feet per second out of a garden hose, which is going to be a very small value. A cubic foot is a lot. If you're thinking in terms of gallons or liters, a cubic foot is a lot. Okay, we'll do a conversion here in a second. But that's a good possible first guess for V. Is that our answer? Well, we don't know yet because we don't have anything to compare it to. Again, we didn't guess an actual volumetric flow rate. We just made a first guess at F, so that'll give us a V, and then we'll use that now to go through the loop. You don't have to start here on the first try. But now we have a V value, I do need to go through the loop. So this gives me a better guess for V. Okay? So if this is my volumetric flow rate, then that means my Reynolds number, using this, okay, so we solved Reynolds number back over here, right? Somewhere. Page 3. We found the Reynolds number. It's going to be 4 times V dot times rho over mu pi d. Or you could find V using you could find the speed here using this value and say rho Vd over mu and be just fine. I don't know what the speed is, and I don't care. We don't need it. This works. So this is going to be 4 times 0.0136 cubic feet per second. I think the units are going to work out, but it's worthwhile the first time to make sure. Density, we said back over here, we looked the density up earlier, we found that to be 62.42 pound mass per cubic foot. Divided by viscosity, we said the viscosity to be 1.038 times 10 to the minus 3 pound mass per foot per second, divided by pi, and divided by this diameter. And if you want to convert this to foot at this point, say, Steve, I'm tired of carrying around 3/4 of 12. Okay, that's fine with me. It's not going to hurt my feelings, though. Or if you want to say, you know what, Steve, this, the only thing that changes is the V dot. Let's do that, guys. Let's simplify. Let's say the only thing that changes here is V dot, so let's multiply everything else together. So if I took 62.42 and divided that by 1.038 times 10 to the minus 3, and divide that by pi, and divide that by this 0.75 divided by 12. That's 3/4 divided by 12. Right? Now, did I multiply by 4? I don't remember. 4 times 62.42 divided by, I don't think I multiplied by 4. Divided by 1.038 e to the minus 3. Divide also by pi, and divide by the diameter, 0.75 divided by 12. There we go. No, I did not multiply by 4. So, Reynolds number is going to be V dot times this 1.225 times 10 to the 6. And if we look at the units there, the pound mass goes away. I've got foot per second. Yeah, it's going to be okay. It's going to be seconds per cubic foot. All right, so that's going to be my Reynolds number, which we know we've got a guess here for my volumetric flow rate. So again, I've just multiplied everything that's not going to change. So if I multiply my volumetric flow rate by that, 0.0136, I'm going to have a Reynolds number there of 16,000, 16,660. Okay, that's turbulent, which we said earlier. We guessed it was probably turbulent. And what does that do for us? Well, again, we're going through this process here. All right, we're going through this process. Now I've got a better guess for volumetric flow rate. Now I've got a better guess at Reynolds number. I've got epsilon over d somewhere in here. Here's epsilon over d. Right? So now I can use that to find an F value. So we go back to the Moody diagram. This is my second guess. I'm going to do it in a different color. Okay. What do we say here? We said this is 1.7 times 10 to the 4, basically. So just shy of 2 times 10 to the 4. So we're back here. We're just barely in the turbulent region. We're up in here. And you can see epsilon over d is going to be in here somewhere. So they kind of all converge together. So we're going to have a much higher friction factor because we weren't near as turbulent. So now I've got a better guess at F. That's a good stopping place. We'll pick up and finish this problem out. Loud pop.